Yeah, sorry for the pause. Yeah, somebody just called me and then I had to enter. Yeah, sorry. So where were we? So these are the two cases. These are, we get the incorrect transmission. Remember that x and e and f are all random now. So your x is given, and then you take fx with this random, and then add e, and then take the g. And the probability that this is different from x is that one of these two cases happen. So this is super event. So the first one does not necessarily, okay. In this case and in this case, both of them, we actually get the incorrect transmission. And if we get incorrect transmission, one of these two happens. So the first case is that when E has bigger than n times p plus delta digits of 1. But what's this E? The number of digits in who has 1 in this E follows from the binomial distribution. So you consider the, indicate a random variable for each digit to be 1. And then you add them. Then that's exactly the situation that we have in Chernoff bound. So use Chernoff bound. Then we show that this happens with probability 0 of 1. So the first case happens with the probability 0 of 1. For the second case, we consider, say, x and x prime, which are different. Let's say, we consider x prime, which is different from x, and which is m-digit string. So x is our random choice, and x prime is for other. And let's say g is the difference, which is not 0. Because this is not 0, at least one digit is 1 gi is 1. So let's say, assume mth digit is 1. Then, if we fix E, and let's say BE with a set of give me a moment. Set of vectors which has Hamming distance and most n times p plus delta from B. So now what we do consider is we fix E and we fix f u1 to f um minus 1. Assume we fix this. Then the vector choice f of um is independent of this. It's still uniformly random. So what's this? If you consider fg, this distribution is determined by this. So even if we fix this, so this fixing, fixes this value, but the last one is not fixed, which is independent from the previous one and which is uniformly random. And then that determines that by the addition of some values of this together with this. Remember that we assume m's digit is not 0, so we actually add this. So this is uniform vector once we fix this. So what do we know then? The probability that the f of g is in BE is what? You consider all possible E and possible f u1 and f u m-1 and probability that the f of g is in BE, assuming those events. This is equality, and watch this. By this analysis, that's because this is at uniform. This is B of E times 2 to the minus n with this fixing. What I wrote down is not correct because you have to actually multiply the probability that all this fixing happens. So this is exactly this. But each one of them is this, and then you multiply that, then you actually get exactly this number, because this summation sums up to 1. So now what? We know that this is a group code, so f of g is f of x minus f of x prime. So what's the probability that the wait. Yeah. Sorry. Yeah, I see something has been not good. No, give me give me a moment. Let me organize my thoughts. Yeah, I think the E here is not really necessarily to be the random vector. Let's say you consider a set of vector f. Then you consider the probability that it's in that set of vectors boundary. Then the probability that fx is having distance at most n times p plus delta from fx prime is at most the probability that this is in B of the zero vector. Which is, you can estimate the size of this, which is 1 plus little of 1 on the exponent of 2, and you take the entropy of this and you multiply 2 to the negative n. So from here. So this is the probability, but we take union bounds for all x prime which is not in x. So here, so we fix E and we fix X as well, and then F is only the random bits that we are considering for now. Then we take the union bound, and the probability that the second event happens is at most 2 to the m times the above probability, which is 2 to the minus n times epsilon over 2 plus root of 1, say, is root of 1. So, second case also happens with the probability small. Because here, I mean, we fix E, X, and this, but the last one. So everything is fixed, and then last one, and you did this analysis. And such a case, you have a probability small. So once you don't fix this, again, you do the similar analysis. You take out the fixing ones, and then probability, and then this probability is small. And you also consider the union bound here, this union bound inside of this formula. But at the end, then you can show that this probability, when everything else is also random, is small. So the first event and second event happens with a small probability. So total probability for incorrect encoding is 0.1. So it's smaller than epsilon for sufficiently large n. And what's this probability? This probability can be rewritten as we consider all possible. So this is the number of functions that we can choose. Each fi is, 2 to the n many choices, and there are m such choices. And we choose f probability, and x and e are random. And we know that this is more than epsilon. This implies that it is the function f such that with this function, if we let x and e at random, then probability of incorrect transmission is small. So this proves what we want to prove. So yeah, so we learned about this code, and here again the usage of this entropy function was roughly as I explained here. So we have this information about x, which is chosen with the m bits, and some other random number e is added, and we want to encode this full information into n string. So that's roughly same as what we want to do. So here you encode and here you decode. If everything is perfect, then that's ideal situation. But allowing some small error probability, we still want to ensure that the number of bits of information these carries are similar. This is m digit and this is n digit, but how many this random variable, how many information does it carry, is roughly this entropy of p times n. So that's roughly how can you understand this Shannon theorem is. If you have m bits information and you want to encode into n bits, then you can still endure the disruption, which is up to different many bits of the information. So next time we will consider, we will further learn about other, types of problem, which also uses this entropy function, and then probably we will, more properly define entropy and then see what properties it has. Probably at the end of next lecture, or maybe lecture after that we can, actually properly learn about the entropy.